My name is Frederick Warburg, and I will present our work on depth completion for active stereo systems. Active stereo systems are widely used in robotics applications that require 3D information. There exist several consumer products that employ this technology, such as the Kinect and the RealSense. The system consists of a stereo pair of cameras and a projector that emits light onto the scene that makes it easier to estimate the disparity between the cameras. However, this resulting disparity map suffers from artifacts and is not dense. In this work, we present a method that corrects and densifies this disparity map. Most depth completion methods have focused on densifying sparse LiDAR measurements due to the popularization of the Kitty benchmark. More related to our work is Active StereoNet, that proposes a self-supervised network to estimate depth from stereo images with an active pattern. Less work have focused on depth completion using 3D landmarks obtained from a SLAM or SFM pipeline. This is a much harder problem due to the low density and non-uniformity of 3D landmarks. In this work, we present a method that effectively uses all three input modalities. Since it is challenging to obtain reliable ground truth data, we develop a self-supervised method. Our method uses three input modalities, namely 3D landmarks obtained from running a SLAM system, semi-dense depth from an active stereo sensor, and infrared images to guide the initial depth estimates. Our model leverages the interleave mode provided by RGBD cameras, where a textured pattern is projected onto every second frame. The active stereo sensor produces a semi-dense initial depth map for the frames with the projected texture. We run a SLAM system on the frames without the projected pattern, which provides us with accurate 6 degree of freedom poses and 3D landmarks. We adapt a channel exchanging network as our backbone. The channel exchanging network takes the three input modalities and output a dense depth map. We choose this architecture as it allows the network to effectively combine the three inputs by exchanging channels at all stages of the network. For self-supervised training, we use a photometric loss between the stereo images and the temporal images. Furthermore, we minimize the L1 distance between the predicted depth and the input depth from the 3D landmarks and the initial depth in the regions where it is available. Lastly, we add a smoothness loss to avoid the aperture problem. Taking the minimum over multiple photometric losses can effectively remove occluded regions from the loss. Taking the minimum over both active and passive losses, however, removes all signal from the active loss. Instead, we propose to take the minimum over only passive losses to keep the signal from the active pattern. The first column shows the infrared images, where the 3D landmarks are overlaid the left image. The second column shows the semi-dense disparity maps from the RealSense sensor, and below the predictions from Active StereoNet, which is the most similar method to ours. The last column shows our method with a ResNet 18 and a ResNet 50 encoder. The video shows that our method provides much crisper results than Active StereoNet. Our method's predictions are also consistent in 3D. In this video, we compare our predictions to the depth estimates from a RealSense sensor. Notice how our dense depth estimates results in a dense 3D reconstruction. Common failure cases of our methods are thin objects and bleeding artifacts. This is a common failure case for self-supervised depth estimation methods, and there exist many works addressing these general issues. We plan to integrate some of these in follow-up works. In conclusion, we present the first depth completion method for active stereo. Our system leverages the interleave mode and uses an image to complete the sparse depth from 3D landmarks and a RealSense sensor. Our method is trained self-supervisedly and produces accurate and dense depth maps. We thank you for your time, and please reach out if you want to hear more.